take that, plug that in here, square it, and you get another 1/9 x squared, wouldn't you? Are we good or not? It's all right? These are all common or like terms, right? So how many ninths is that over there? 9 ninths plus 1 ninth. 9 ninths plus 1 ninth plus 11 ninths equals 4. We agree? Multiplied by the reciprocal. X squared should be 36/11ths. And now take the square root, right? And when you take the square root, you have to do plus or minus. And you take the square root. So when I do that, I should get x is plus or minus the square root of 36 over the square root of 11, which I'll just leave as root 11. Right there, we've nailed down what x is. X is either positive 6 over root 11 or negative 6 over root 11. Now, how can I get y? Remember what y was? I just erased it. It was 1/3 x, wasn't it? So multiply this by 1/3. What would happen if I multiply? Oh, sorry. Let's do this. There's two cases, right? Here. Let's suppose x is the positive one first, and then we'll come and do the negative one. If x is positive 6 over root 11, then y must be 1/3 of that, right? Which is just 2 over root 11. And then z must be negative 1/3 times x, so negative 2 over root 11. That's from here. So I have an ordered triple, don't I? I have x, y, z. So here's what I've got so far. I know that if x is 6 over root 11, then y must be 2 over root 11, and then z must be negative 2 over root 11. Right? That's my x, my y, my z. Something interesting is happening there. I don't know yet what is happening, but I know that that's an interesting point. You following me? Now I need to look at the other case. What if x was negative? The y would be negative, and the z would be positive. So all that would happen is this would change to negative 6 over root 11, negative 2 over root 11, and then 2 over root 11. And from the geometry of the problem, there should be 2 points that we're going to find here, right? One of them is furthest away, the other one is closest. And we have 2. Now, before I stop and we find out, which of these corresponds to the maximum distance or closest and furthest, whatever, we did say suppose x, y, and z weren't 0, right? What if they were? What if x, y, and z were 0? Fourth equation wouldn't work, right? So if x, y, and z are all 0, then your fourth equation is not satisfied. So we can throw those out. Understand? Now you could write that down, to be technically correct. Suppose x equals y equals z equals 0. If they're all 0, equation 4 would say x squared plus y squared plus z squared equals 4. That wouldn't be true, right? So we're done. I never found lambda, did I? Could you? Didn't we solve for lambda earlier? Didn't we solve for lambda earlier? Lambda was like, we solved for it 3 different times. It was x minus 3 over 2x root junk, right? Well, if you plug in x, y, z into here, you would find lambda. I'm going to pass on that, okay? Lambda here is something, but I know I could find it, right? And here, lambda is something. It could be a different lambda for this. All right? I don't care. I care about x, y, z. All right, so let's do it. Let's try and figure out which one of these is furthest, which one of these is closest. That might be a little tough. So my function f, I'm going to plug in, let me plug in the 6 over root 11, 2 over root 11, negative 2 over root 11, and I'm plugging that into the square root of x minus 3, 6 over root 11 minus 3 squared. Do you understand where I'm putting this? 2 over root 11 minus 1 squared, negative 2 over root 11 plus 1 squared. And then I have to figure out what that is, right? And I'm going to cheat because I don't feel like using my calculator. I believe I already have my computer do this. I thought I did. This turns out to be about 1.316. Okay? And the other one, if you plug in negative, negative, positive, okay, into this, the other one turns out to be 5 point something. So if you do f of, I'll stick with black. The green doesn't show up on camera very well. If I do f of negative 6 over root 11, negative 2 over root 11, 2 over root 11, you get approximately 5 point, I don't know, 5.31. 6. So this point right here, right? This point right here, well, I should say this one. This one right here is closest, isn't it? And this one right here is furthest away. And both of these points live on your sphere. Got it? I can't think of another way you would do that problem without Lagrange multipliers at this point in this class. Like, that's all you've got. Now, I do have a demonstration that shows you kind of like why Lagrange works, but because of time, I'm not really going to go into it. If you want to see it, you can come in my office and I can show it to you. It only works for, it's a way to try and convince you that this works, but it's only going to work for the two variable case, like f of x, y. Once you get past that, you just kind of have to, you can't get into it visually at that point. Okay, moving on. What did y'all think of that one? All right? Sucked? Glad to be back? Yes? Yes to all those? All the above. So I'm not doing quite a few problems here. Like I'm not doing these first two examples I was going to do in class, but I'm going to leave those for you. And there's problems in your homework that you'll get some more practice with this. The challenge again is going to be the solving of the equations. How are you going to go about doing that? There's no like always do it this way, or you just got to play with it. How about this one? Maybe we can talk about this one without actually going through the whole thing. Maybe just set up what's the objective function, what's the constraint. Find the maximum volume of a rectangular box with no lid if it is to be made of 12 square meters of cardboard. Does this look familiar? This is a Cal 1 problem. This is a Cal 1 problem. You can do this. You can do this with Cal 1, but it's easier. It's easier in Cal 3. It's much easier. Okay. So what are we trying to find the maximum of? Maximum what? Volume. What's the volume of a rectangular box? Length times width times height. So why don't I call it x, y, z? Is that okay with you? Does that make you happy that this is going to be a function of three variables? X, y, z? Yeah? Okay. Constraint. All right, so let's talk about the constraint. This box has no lid. There's your box. It has no lid on it, right? So you can put your hand in there. But it has a bottom to it. We know the volume. If we call this x and call this y and call that z, we know the volume is x, y, z. But it has to be made from 12 square meters of cardboard. That means the total surface area of this has to be 12, right? That's a constraint, isn't it? That's a constraint. What's the surface area of this thing? So what's the surface area of this front face? xz. How about that back right there? xz. So I know that 2xz's plus, how about this side right here? Y times z, this side, y times z. I know that 2 of those plus the bottom, okay, what's the area of that bottom piece? Just one of them, xy, because it didn't have a lid, right? That must be 12. Objective, constraint. You go to town now. Understand how that sets up? Actually, in Cal 1, you couldn't do this problem. The way they present it in Cal 1 is they give you a sheet of paper, and you like cut out corners. Does that look familiar? Maybe you didn't. You may or may not have seen it. It just depends on your instructor and whether or not you got to it. But that's different because you're cutting squares out of the edges, and that's a little bit of a different problem. So, all right, let's look at another one. I'm not going to work through that one. Find the maximum volume of a rectangular box with double bottom if it is to be made of 81 feet of cardboard with a double bottom. So it's the same picture, right? Except they're going to reinforce the bottom with 2 sheets of cardboard, which is the same as having a top to it, isn't it? Yeah. All that changes is this. And then this is what? 81? There you go. Same exact thing, right? Except change that to a 2. Or, oh wait, it doesn't say it has a top. Does it say anything about the top? Just double bottom. So what do y'all think, 3 or 2? I think 3. Don't you? They didn't say no lid, right? So we should assume lid. So it'd have a lid and a double bottom. So then that should be a 3. Take that back. Thank you, Luke. But you get the idea, right? I mean, it's just a matter of interpreting the problem, converting it over to the math now. We just did that one. Okay. Now this, I don't have an example for, but I think I might do one. It just depends. I'm afraid to get into one because I'm afraid of how messy it might get. But let's say that you have a function of 3 variables, and you want to constrain it, but give it 2 constraints instead of 1. I'll give you an example just real quick, just thinking about it. Remember that sphere we just had, right? And we had a point, and we found the point, the 2 points that were closest and furthest away from that point. What if I came through, we know this has a constraint equation. It was x squared plus y squared plus z squared equals 4, right? That's what it was. What if I said, take a cylinder and pass the cylinder through your sphere somewhere. It would cut through, wouldn't it? And it would create like a little path on top, like a little ellipse or something on top, or a circle on top, yes? And you would have another one on the bottom where it cut through. And now my question is, what points on the intersection of these 2 surfaces, on that little thing and on that, which points on those things are closest to this? Understand? So the way this works is that you have 2 constraints now. You have to live on the sphere, that's your first constraint, but you also must live on something else, which in this case would be a cylinder. And then Lagrange has a way you do that. The Lagrange method for this is that you set the gradient of f equal to, well, this part is exactly the same, right? Lambda times gradient of g, but then you say plus another constant, mu, times the gradient of h. How many equations will you get from these right here? You get 3 from this, and then 4, and then 5. You'll have 5 equations. You're solving for x, y, z, lambda, and mu. 5 equations, 5 variables. Would you like to see one of these? Okay, let's pick one out of the book. And I think I'll do a word problem if I can find a good one. And I just hope it's not going to be too hard. Okay, yeah, this one looks okay. I'm going to do the example right out of the book. That way we're playing it safe. Okay, so what we have is we have a function. The function we're given here is x, y, z is x plus 2y plus 3z. It says find the max of this, okay? Find the max of this function on the curve of intersection of the plane x minus y plus z equals 1. That's the equation of a plane, isn't it? Okay. And the cylinder x squared plus y squared equals 1. Okay, so geometrically, if I can try this, what we have is a cylinder, okay, right there, and we have a plane. I thought I saw a bunch of other colors in here. Let's see, red, try this. We have a plane, right? And we're assuming that this plane comes through and cuts through this cylinder, right? And creates, wow, that's terrible. Just say it cuts through somewhere, all right? And where it cuts through, it creates a curve, doesn't it? And there were problems that we had in the past where you were asked to find the vector equation of the curve, right? Intersection of two things, and you did that. What we're trying to figure out, though, is that if you take just the points that live on this intersection, these all have x, y, z's. You take each point and you plug them into that function, what's the biggest value you're going to get out? So your domain is actually just the points on this curve. You're constrained to that intersection, but you're plugging those into this function. What's the biggest thing that comes out? All right, so understand you have two constraints then? All right, let's write down, let's call this one G. The left side's G. This one is H, isn't it? And so let me write down my equations. The first one, I need the partial of f with respect to x to be equal to. Let's see if you can pick this up without me really giving you time to write any of that stuff down. That has to be equal to lambda partial g with respect to x plus mu partial h with respect to x. That's the first equation I'm going to have. Second equation. Partial f with respect to y plus, sorry, not plus. Partial of f with respect to y equals lambda partial g with respect to y plus mu partial h with respect to y. The third equation, yes? Nope, it's just lambda times the g. That's it. And this is just mu times the h. Okay, third equation.